No more funny accents, please.
There's probably people in
Dew point, the temperature at which air will become saturated, or the temperature to which air needs to cool down to become saturated. Last class I was saying, think of a bucket. If you have a bucket that's partially full of water, if you cut off the top of the bucket and then cut off a little more, keep cutting it off until you've gotten down to the surface of the water. That's like the dew point. But as you make it smaller and smaller, eventually it's going to be full, and that's like the dew point. Yeah?
On the test, can we refer back to the bucket?
Yeah, you can refer to buckets.
Do we have a test today?
No, it's next class. And it'll be halfway between a test and a quiz, just in terms of point value. Number 4, the relationship between air's water vapor capacity and temperature. Hot air can hold more vapor than cold air. And that's where I use my graduated buckets. This would be like hot air, and this would be like cold air. So this has got a bigger capacity, that's got a smaller capacity. The reason for that, in order for something to be a gas, it needs energy. Gases have more energy than liquids, and hot air can provide more energy than cold air. Water needs energy in order to be a vapor or a gas. Hot air can provide more energy than cold air can. Number 6, what happens to the relative humidity as air heats up? So with my drawing that I've already got here, if I put some water in here, this would be the absolute humidity I'm representing now. And you go from colder air to hotter air, so it's heating up. It's getting more full or less full? Less full. So relative humidity decreases. And explain why. Heating causes the vapor capacity to increase. Now this is assuming that I'm not changing the absolute humidity. I'm not changing the amount of vapor in it. If the capacity increases and you don't change the amount of vapor, then it's going to be less full. So if you need me to slow down or anything, let me know.
Did you explain
5.
I just got
Yes. So this is hot air has a lot of energy, and it's going to be able to provide heat to water to evaporate it and put it into gas phase. And cold air doesn't have as much energy, so if you have a puddle, it's going to be less able to heat up those water molecules in the puddle and make them evaporate. So the water that's in the air as a gas has a lot of energy, and if the air cools down, that's going to lose energy, and some of that water has to come out. So hotter air has more energy, allowing more stuff to turn into a gas, which is a high energy state of matter. Liquid is a lower energy state of matter. Number 8, I already did that. No, I didn't. So number 6 and 7 are kind of like 8, except 8's adding this extra layer of complexity on it. For a question like this, I may ask you, instead of rises, I may ask you about sinking. And all you really have to know here is when some air rises, what does that do to the temperature? It makes it cold. So the relative humidity increases because rising air cools, and cooling decreases the capacity of the air because it has less energy to turn water into a vapor or keep water in vapor phase. So it becomes fuller. So this diagram that I've drawn, this would be, fuller. So this would be like what would happen to air as it rises. The air is hot when it's lower down, it goes up into the atmosphere, and it cools off, so its capacity decreases, but the fullness increases. 25%-ish relative humidity to maybe 40% here. Number 9, I'm going to think through this with circle the word rises. And circling things that might go either way on a quiz. I might ask you about air sinking, and here I might ask you about air cooling off. And here I might ask you about humidity decreasing. Yeah. So describe a situation in which humidity increases while temperature remains constant. So I'm going to draw some air of constant temperature. So this is going to be warm air, and this is going to be warm air. I'll just draw the warm air first. How should the warm air look? Bigger or smaller or the same size? Same size. So if the temperature determines the size of my bucket. The size of the bucket is representing the capacity for water vapor. And if the temperature is remaining constant, then the capacity is staying the same. Buckets are the same size. But I've got relative humidity increasing. So I'll just randomly put a certain amount of water vapor into this bucket. If relative humidity is increasing, what should my water vapor look like in this bucket?
More full.
It should be more full, so like this. So now the question, so this is what's happening. We've just figured out that the capacity is staying the same, the fullness is increasing, and actually it turns out that the absolute humidity has to be increasing too. So now the question is, how can that happen? How could you get more water in? There's more water vapor in this air than there is in that. Temperature's not any different, but there's more water vapor in it. How could that happen? What? Could go over an ocean. It could just be in a room with some little puddles. It could be somebody's got a water bottle and they're going pss, 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 spraying this spray of water in the air. But one way or another, there's water evaporating, being picked up by this. This is like a towel. This is like a towel that somebody has dried up an extra couple of puddles with. So my answer is, when air evaporates water from the Earth's surface, vapor is added to the air. So it could be coming from the surface, it could be coming from whatever, somebody spraying water into the air. It could be coming from puddles, rivers, lakes. Number 10, when do we reach the dew point and why? I said early morning, but if you said night, that's okay. The idea is just that you're going to reach the dew point when it's coldest. And early morning is the coldest time. And you reach the dew point when it's coldest because as the air cools off, its capacity gets smaller and smaller and smaller until eventually its capacity is so small that it's going to be full. It's going to reach the point where the top of the bucket is equal with the top of the water, and then you've reached the dew point. Can I flip?
Wait, can you go back to the top? I didn't get 1 and 2. Yeah, no, I don't think I said that.
Actually, you know what? Let me just give it to you later if you need it. I'm going to scan this and I'll put it on my website too. So number 11, what happens to the relative humidity of air that travels from outside into a heated house during the winter? Explain why. Even now, even though it's so warm, it's still colder outside than it is inside. But when it gets really cold, this effect gets really strong. So here's the house. It's a really nice house. And this is the air outside the house. And the relative humidity out, I used to think, oh, it gets so dry in the winter. But it doesn't really get dry in the winter. It's just that when the air moves into the house, it gets dry. So you have air outside. Let's just say it's 50% relative humidity. What happens when it comes in? Does it warm up or cool off?
Warm up.
Yeah, it warms up. So, oops, I made my air too big. It won't fit in the house. Okay, here's my air. 50% relative humidity. Comes into the house and it warms up, and what that changes is the capacity. So now it's got a greater capacity, but it hasn't really picked up any moisture. So now the relative humidity has dropped. So relative humidity decreases, fullness decreases because the air heats up, increasing capacity, decreasing fullness. Stop giggling. You didn't pay attention. Do you have your sheet somewhere?
Yeah, I did. Okay.
Number 12, there were a couple of them I added at the last minute. This was one of them, and I kind of regret not giving you, I could have even given you numbers for relative humidity. I could have had 0%, 100%, and then it would have been a lot easier. And I could have done that same thing for humidity, but hopefully you have a similar kind of pattern. So humidity, all you have to do is look at the water levels. They're the same, goes up, stays at the same level, goes down. So this is the actual amount of water vapor in the air. Stays the same, goes up for a little while, stays the same, goes down, and then it goes down again, and then it stays at that same level the rest of the time. And then relative humidity starts totally full. This would be 100%. I could do a dotted line across for 100%. And now it's a little less full, so the relative humidity decreases. And then so that's 75%. And then it becomes even less full. Now it's at 50%. I didn't do this quite right, you can tell. And then it gets a little more full, and then it gets even more full, and here it's totally full. And this is kind of weird because this is getting smaller, but that's staying constant. As the air cools down, it's reached the dew point here, and as it gets colder and colder and colder, the dew point lowers, it stays at 100%. It can't get any fuller than 100%. It's just stuff is flowing out as it's cooling off. And then it starts to get a little less full again, and then a little less full back to 50%. So if your graph kind of goes the same, up, down for humidity, and if it goes down, up, down for relative humidity, you did a good job. Any questions about that? Number 13, heat pump has a condenser and an evaporator. What happens in each one? There may be more, you could say more, but the important thing is that in the condenser, the refrigerant condenses. And in an evaporator, the refrigerant evaporates. And you don't have to say it turns from a gas to a liquid or liquid to gas, but I did, just to be extra to the point. And you could have said even more too. You could have said as soon as something enters, as the refrigerant goes into the condenser, it heats up because it passes its compressor, which heats it up. And as soon as something enters the evaporator, the refrigerant enters it, it cools off immediately. So I left that out, but this is the important thing to focus on here. And I think this is confusing, but it's not so bad if you just think about sweating. If you think sweat evaporates, that makes us cold, you can remember the rest. So the evaporator, which one's hot and which one's cold? The evaporator's cold, and the evaporator's cold because evaporation absorbs energy. The stuff that's evaporating needs to take energy. It needs to absorb energy. And if it's absorbing it, it's robbing heat from everything around it, making everything around it cold. And that's why sweating, when sweat evaporates, that makes you cold. And then the condenser is doing just the opposite. It's hot because condensing releases heat. So you have this, in the condenser, you have this gas, which had a lot of energy, turning into a liquid, which has less energy, so it's releasing heat and heating up everything around it. 15 or 14, the purpose of the compressor is, this is really the most important purpose. It increases the pressure so the refrigerant will condense. When you increase pressure, you make it less, you make it harder for stuff to boil. You make it easier for stuff to condense. It just turns into a liquid from a gas easier. But you could also say that the purpose is to heat up the condenser. So the compressor heats up the condenser. If you want to heat your house, you need to have something that's hot, and the condenser is that hot thing. And it needs to be hotter than your house in order to heat it up. So you could give that as a reason too, or a purpose. And then the evaporator, somebody last class pointed out that I'd answered this question wrong. I was thinking that 14 and 15 were kind of opposite questions with opposite answers. So the compressor, yeah, but the compressor heats this up, and the evaporator cools it off, but it's not really the evaporator. The evaporator is not analogous to the compressor. What should I have put here? What's the expansion valve? The expansion valve is what causes the evaporator to cool down. The compressor is what causes the condenser to heat up. So I said these things a little funny. So I had to change my answer. What's the purpose of the evaporator? Is to provide a low pressure environment so the refrigerant can evaporate. And to cool down the evaporator, that doesn't really make sense either, because it is the evaporator. It's just to cool down. To get cold. So if I had to do over again, I'd change that to expansion valve. And the answer would be to lower the pressure so the refrigerant can evaporate, and it would be to make the evaporator cold. So last class, we talked about something that I think might kind of help. We were talking about if you stepped out of a spacecraft into the vacuum of space with no spacesuit on, what would happen to you?
Well, you could
And it's related to this.
You could survive for like a couple seconds, like you'd be fine for a couple seconds, and then all of a sudden, like your eyes would like suck out of your head, and
Why would your eyes suck out of your head?
because the pressure inside is different.
Do you
than the
have
pressure
giant
outside.
air pockets behind your eyes with pressure in them? When there's no pressure outside your eye, that would suddenly shoot them out.
I don't know. It's a movie.
That's actually kind of
now,
fun to
if you
see.
if you had air-filled eyes, if you have inflatable fake eyes, those are going to pop as soon as you step out of the spaceship. If you take a deep breath of air and you duct tape or gorilla tape your mouth shut and your nose shut, and then you step out of the spaceship, what's going to happen? You're going to pop, or the tape's going to pop, because inside the spaceship there's pressure. Inside your body there would be pressure. When you stepped out, outside the body there'd be no pressure, but inside there would be, so you would pop. But if you didn't do the duct tape thing, you'd just kind of go, and the air would come out of your lungs. Then what would happen?
You'd,
Yeah?
you'd suffocate, probably.
You'd suffocate. How long would that take?
3 minutes.
Usually, I think
But-
four-ish minutes to have brain
Wait,
damage.
not over
Yeah.
yet.
Brain death.
There's another unpleasant fate. Space is very, very cold.
Now, it is cold. It's cold, and the fact that space is cold means that if there are molecules in space, how fast are they moving?
Not very fast.
Not very fast. Now, would there be molecules around your body if you stepped out into space?
Yeah.
What's
No.
it? No.
No,
Space
space
is
is
a
nothing.
vacuum, pretty much. So you step out of the
Space is nothing.
spaceship. Is there anything touching you to take your energy?
No.
No. So it wouldn't be like stepping out and touching a cold pipe, and heat would flow out of you into the pipe. Would you have wind blowing across your body, taking
No.
heat away? No. So the only way you would lose heat is not through conduction, not through convection, but through radiation. Maybe some convection, because you might start bleeding, and that might sort of fly out into space. In fact, that's really my point. That the most relevant thing here is when you step out into space, the pressure that was pushing all of your body, that's gone. So it's going to be like your body's getting sucked on. Your body would sort of turn red, like you're getting a big hickey all over your body. And the most vulnerable part of your body, there are two parts. One's your ears. What would happen to your ears?
Boom.
They would pop outward because you do have air in your ears, and that would expand and pop your eardrums
That'd be
out.
kind of cool to see.
And the other one is the capillaries of your nose and maybe in your eyes.
Oh.
So you'd get an instant nosebleed, and because there would be no more pressure pushing against those capillaries close
Could
to
you
the skin.
pop your? Could
So
you,
I feel like this could be on American Horror
So
Story.
the blood would come out, and immediately your blood would do what?
freeze.
No. Well,
No.
what would it do first?
It would boil.
It would boil. And the boiling might cause the rest of the blood to freeze, because as the first blood comes out and there's less pressure, the blood has a lot of water in it. And the water molecules are moving, and they can't fly away and boil normally because of gravity holding them down and intermolecular attractions and pressure. But you remove the pressure, remove the gravity, and they suddenly start to fly. So your blood would start to boil. And when it boiled, it needs to gain or lose energy to boil. Gain. So it's going to take in energy. It's going to start to get cold, and that might freeze the other blood. It might not all boil off before some of it freezes, but eventually that would sublimate too after you're dead. But so immediately you get nosebleeds, and you'd also pass out. I don't know exactly what the mechanism is, but I've heard you'd pass out, and so you wouldn't get to see your blood
What is the
boiling.
reason for that? Why are you popping?
Sure
Ground
about
control to
the
Major
pass
Tom.
Maya.
If you're in space when you're like in the mat,
What?
you were saying before about like everything exploding.
Yeah.
Would your internal organs explode too?
Anything that has an expandable gas in it that's under pressure normally would expand when there's no pressure on the outside. So if you had gas, on a particular day you got little gas bubbles of various sorts in there, you would have severe gas pains when the
So could you,
pressure disappears.
Could you like?
They would expand a lot. Great.
Could your organs like start coming out of your mouth?
Well, I showed you the swim bladder of fish, right?
No, you didn't.
Yeah, you
Yeah.
did.
Yeah.
That happens with some fish. They have a swim bladder which has gas in it, which allows them to regulate their depth. And when you pull them up from the deep really fast, that expands and comes out their mouth. And then you can't catch and release at that point. If you had a swim bladder, but no. Your lungs, the easiest way for air to come out of your lungs would just be through your mouth, through your nose. So. But if you duct taped, if you wanted to do that to yourself. But then there'd be no way for them to get out. So I think you'd probably just, I don't know if you'd actually pop. I don't know what that would look like.
That'd be painful.
Let me get to the point of all this. The point was to come up with a different situation where this was happening. So in the evaporator, it's making it like the vacuum of space, really low pressure, so you get evaporation or boiling. There's a fine line. Evaporation and boiling are both things turning to a gas. It's just boiling. Everything is doing it at once. Evaporating, it's a few molecules at a time. Let me move on, though.
Hey, completely unrelated question.
Well, let me finish and write it down so I don't forget. Number 16. Refrigerators like a heat pump, where do the condensing coils and evaporating coils need to go? So I called it the condenser, but I should have written condensing coils. They're hot. They need to go outside the fridge. The evaporating coils, they need to go in the fridge because they're cold. So you put the cold stuff inside the fridge, the hot stuff outside the fridge. Kind of common sense. What's not common sense, though, is why the condenser becomes hot. But hopefully you know. Now this last one, this was another one I added at the last minute. And you were supposed to trace the flow of the heat. And just think about the heat moving from warmer places to colder places. And the whole idea of a heat pump is, in the winter, you want to pump heat into your house. In the summer, you want to pump heat out of your house. But exactly how does it get there? It's always got to go downhill. So this diagram, you need to start by looking at the compressor. And that tells you where the condenser is and where the evaporator is. So this gets compressed. This is going to be hot because stuff's condensing in here. This is going to be cold because it's expanded, stuff is evaporating in here. So you can go in different kinds of directions, but I decided to say, I'm just going to treat this as a cooling system. And this is the cold side, and this is the warm side. So this will be like a house where heat's coming out of the house. It's being air conditioned. So we've got this pipe that goes through your house. It's really cold, cooling your house. Heat goes into that and moves to this thing. The evaporator is super cold, colder than this tube. So the heat goes from here into the evaporator. The molecules that have that heat in them, they just move through here. They get compressed, and then they start to condense over here. So now they're really hot again. And this is much hotter than this pipe is going to be, so the heat flows from here into there. And this hot pipe is much hotter than its environment, so heat exits. So let me try to say it all a different way. This is really cold, so heat's going to go into it. So heat goes from here into there. This is really hot, so heat's going to come out of it. So heat goes from here into this. And from here out into the house. If heat's going into this, it's got to get in from the house. Any other questions about this? Okay, Macy, what was your question?
So, do you know how erasers work? Like, do they, when